Hello guys, in this lecture we are going to study about the unit step function in Laplace transformation. Unit step function is used as a powerful method to find out the solution of the problem of mixed and time dependent boundary conditions. Like in a river, when with respect to time the direction of the river is changed, whether the time is very large, but this is one of the example of time dependent boundary condition, and we are using this in a Laplace transformation. Laplace transformation is used like in a previous unit you have studied a differential equation of this type where you find out the CF for the left side portion and the PI for the right side portion, and finally your solution is CF plus PI. But in this solution we are having the arbitrary solution, arbitrary constant, that is AC, that is C1, C2 and C3 involved. So this is the general solution, or we can say that complete solution. But by using the boundary conditions and initial conditions like y0 is equal to something like sine of x, or y dash 0 is equal to 1, similar like this, by using these type of condition we get the exact values of c1 and c2 a particular values. Then we get the particular solution in which y is equal to a function of x, where c1 and c2 is having a particular value. By using the Laplace transformation we are directly approaching from this step to particular solution. That means the between the step CF and PI and then implementing the boundary conditions and getting the solution for the particular solution is eliminated. So this is just a shortcut and a good method, but it is not applicable on all the differential equations. A unit step function. A unit step function, a function which is represented in the form of ut minus a, as defined as function u of t minus a, is having either 0 or 1. 0 when t is less than a, 1 when t is greater than equal to a, where a is greater than 0. Like this, graphically, this is axis for time, this is the axis for the function value, and function value is 1 and 0. Function is having 0, function value is 0 when t is less than a. For less than a it is 0. As time t approach equal to and greater than a, it will be at 1. It is at 1. So this is the called unit step function. Laplace transformation of unit step function is, that is Laplace of function unit step u of t minus a is equal to, by using the Laplace first principle rule, integration 0 to infinity e to the power minus st and function dt is equal to, now because the function is having a two value 0 and 1, 0 when the integration is from 0 to a e to the power minus st, value of function is 0 dt, plus integration limit a to infinity e to the power minus st, and the value of the function is 1 dt. So first integration is 0, for the second integration e to the power minus st integration will be e to the power minus st over minus s for the limit a to infinity. For the upper limit it is 0, and for the lower limit the value of this is e to the power minus as upon s. So this is the Laplace transformation of unit step function. Now a second shifting theorem. A second shifting theorem is, if the Laplace of function ft is fs, by using the first principle of Laplace of ft is equal to integration 0 to infinity e to the power minus st, and function of ft dt is always giving you the solution in a form of s. That means a function of s. Then the Laplace of ft minus a is a function into u of t minus a is a unit step function. Unit step function is equal to e to the power minus as and the function of s. Function of s of Laplace of ft. This value, the function of fs. Now, to prove this, let the Laplace of function t minus a into u of t minus a is equal to, now the substituting the value of this unit step function, that is 0 to a e to the power minus st, function of f of t minus a is same because we don't know the value of this, into 0 and dt, plus the second limit is a to infinity e to the power minus st, function of t minus a is same, into the unit step function value, that is 1 and dt. So first integration is 0. By using the second integration we get integration a to infinity e to the power minus st, function of t minus a dt. Let we assume t minus a is equal to u. Now we are changing the integration from du to dt to du. So dt is equal to du. Dt is equal to du. So integration when t is a for the lower limit, when t is small a, then substituting the value of t over here we get 0. U will be 0. T is equal to a, u will be 0. When t is equal to infinity, we are getting u as infinity. So the limit of the integration is 0 to infinity e to the power minus of s, and the value of t, from this portion we will calculate, t is equal to u plus a. So t is equal to u plus a, function of u, and dt is changed by du. Now because this is an integration with respect to u, so we can take as e to the power minus st as a outside of the integration. So the integration limit 0 to infinity e to the power minus s of u, function of u du. So this is just the similar of Laplace transformation, first principle of Laplace transformation. Over here we are getting the Laplace for function of t, but over here we are getting the Laplace of function of u, but the result will be function of fs, function of fs and e to the power minus sa. So now we take an example, Laplace of t minus 3 into unit step function of t minus 3 will be equal to e to the power minus 3s upon s square, and if the Laplace of t minus 5 square into u of t minus 5, then it will be e to the power minus 5s over s cube. Now consider the example. Find the Laplace transformation of t square u t minus 3. So t square u of t minus 3, we know that this ut minus 3 is a unit step function. For this t square we try to convert it into the form of t minus 3, so that we will get the term similar to t minus 3 into u of t minus 3, so that we will easily find out the Laplace transform. For this t square, we just calculated the term t minus 3 whole square plus 6 t minus 3 plus 9 into unit step function t minus 3. So finally the function will be t minus 3 whole square unit step function of t minus 3 plus 6 t minus 3 unit step function of t minus 3 plus 9 unit step function of t minus 3. Now taking the Laplace both side, Laplace of t square u t minus 3 is equal to Laplace of t minus 3 whole square u t minus 3 plus 6 Laplace t minus 3 into u of t minus 3 plus 9 Laplace of u t minus 3. So now we get the value e to the power minus 3s into 2 over s cube for this first term, because it is t minus 3 whole square. So over here we use 2 and s cube, we will get s cube. Now for the second term, 6 Laplace of t minus 3 ut minus 3, we get e to the power minus 3s into 6 over s square, and for the last term we get 9. For this term 9 e to the power minus 3s over s. So finally the Laplace of given function ft, if this is the ft, the Laplace of given function ft is equal to e to the power minus 3s taken as a common 2 upon s cube plus 6 upon s square plus 9 over s is the Laplace of the given problem. Now the next question is, express the function in terms of unit step function and find its Laplace transformation, where the function ft is having the value 0 when t is between 0 to 1, function value is t minus 1 when the t is between 1 to 2, and function is 1 when t is greater than 2. For this, like, we have to draw the graph. This is for t and this is representing the f of t. So according to it, when the time t is 0 to 1, when the t is from 0 to 1, the value of the function is 0. So this is the graph, the value of the function is 0. When again, now over here, if we substitute t minus 1 for t is equal to 1, for this value we are taking the lower value, t is equal to 1, we get 0. And when we substitute t is equal to 2, we get t minus 2, that is 2 minus 1 is equal to 1. Over here, for the lower value we are getting 0, for upper value we are getting 1. So over here 1 to 2, at point 2 the value of the function is 1. So for the middle portion, this will be the graph, and the function value is 1 when t is greater than 2. When t is greater than 2, the function value is 1. So this is the required graph for the given function. This is the required graph for the given function. Now we have to find out the Laplace. First we have to express this function in terms of unit step function. So function ft is equal to 0 into unit step function of t minus 0 minus u of t minus 1. This is the term we calculated from the lower limit and upper limit of the value when function is 0 plus u of plus t minus 1 into u of, now the upper value is 1, lower value is 1, t minus 1 unit step function minus the upper value is 2, so the unit step function is u of t minus 2, and for the last plus 1 into, for t is greater than 2, unit step function of t minus 2. Now when we calculate it, we get function of ft is equal to, first term is, this term is completely 0 because it is multiplied with 0. For the second term we get t minus 1 u of t minus 1 minus t minus 1 into u of t minus 2 and plus u of t minus 2. To find out the Laplace, we just have to take this portion as a common and simplify it. Then we will get f of t, function of t, is equal to t minus 1 u of t minus 1 minus t minus 1 plus 1, minus 1 into u of t minus 2. So function of t is equal to t minus 1 u of t minus 1 minus t minus 2 and u of t minus 2. Now taking the Laplace on both sides, then Laplace of ft is equal to Laplace of t minus 1 u of t minus 1 minus Laplace of t minus 2 u of t minus 2. So finally we get the solution of Laplace of ft is equal to, by using the formula, e to the power minus s upon s square minus e to the power minus 2s upon s square. So this is the required Laplace for the given problem, and this is the expression, this is the graph of the required function, and this is the function which represent the given function in terms of unit step function. So this is the unit step function which is over. So thank you for watching this video, and we are not giving any question related to the unit step function in this video, and your concerned faculty will provide you few questions and have a healthy discussion, and stay home, stay safe during this time. Thank you.